Welcome back to AI Paper Podcast. Today, we're going to be taking a deep dive into exploring the limit of outcome reward for learning mathematical reasoning.
Nice.
This paper really digs into how we can make AI, those large language models we all know and love, and math superstars,
Right.
using reinforcement learning or RL.
Yep.
And you know what? They managed to do it using only outcome rewards.
Yeah. Pretty wild, right? It really is. Think about it.
Yeah.
We're essentially training these models by just telling them correct or incorrect at the very end of a problem.
Right.
No hand-holding, no partial credit for getting steps right along the way.
Wow.
It's like giving someone a complex math exam and only telling them their final score.
Exactly. And that's a big departure from how a lot of RL for math reasoning is done today.
Yeah.
We usually rely on more fine-grained feedback,
Right.
which can be computationally expensive and sometimes even impossible to obtain.
Right? The traditional approach often involves evaluating each step of the AI's reasoning, which can be incredibly complex and time-consuming.
Yeah.
This paper explores the limits of what's possible when we strip away all that extra information and focus solely on the final outcome.
So to recap for our viewers,
Yeah.
this paper introduces a new framework called OREAL
Okay.
that's all about squeezing the most learning out of those binary outcome rewards.
Right.
And the results are impressive.
Absolutely.
They achieved a 94% accuracy rate on the challenging Math 500 dataset using a 7 billion parameter model.
It's worth highlighting that this is the first time a model of that size has achieved such high accuracy using only outcome rewards.
Wow.
And they also pushed the boundaries further with a 32 billion parameter model, achieving a new state-of-the-art accuracy of 95%.
Those are serious numbers. Now, I know our audience is full of AI enthusiasts who love the technical details.
Oh, of course.
So let's dive into how OREAL actually works.
Okay.
Kind of the key components is something called best of n sampling.
Best of n is an elegant approach that's perfectly suited for this outcome-only environment.
Okay.
Essentially, the AI makes multiple attempts to solve a problem, and we only focus on the most successful attempts during training.
So even though the AI might stumble along the way,
Right?
OREAL helps it zero in on the strategies that actually work.
Precisely. It's like sifting through a pile of solutions and picking out the gems, the ones that lead to the correct answer.
Interesting.
And the really cool part is that the researchers mathematically proved that this approach guarantees the AI will eventually converge towards the optimal way to solve these problems.
So we're not just hoping for the best.
Right.
There's a theoretical foundation ensuring we're on the right track.
Exactly.
That's reassuring.
Yeah.
But what about all those attempts where the AI doesn't get it right? Does OREAL just discard those?
Not at all. Remember, even in incorrect attempts,
Yeah.
there might be parts of the reasoning that were actually on point,
Okay.
and that's where reward shaping comes in.
Okay, reward shaping, that sounds intriguing.
Yeah.
How does OREAL use that to learn from mistakes?
It cleverly adjusts the rewards for incorrect attempts.
Okay.
Imagine telling the AI, hey, even though you messed up the final answer, these specific steps in your reasoning were actually pretty good.
Interesting.
It's like giving partial credit after all, but in a more targeted and strategic way.
So we're not just throwing the baby out with the bathwater.
Right.
We're extracting valuable lessons from those missteps.
Exactly. And the researchers derived a specific formula for adjusting those rewards, ensuring consistency between how the AI learns from both its successes and its failures.
Wow.
It's a really elegant way to make the most of every bit of information.
I like that, squeezing every drop of learning from those precious training samples.
Yeah.
But we're still dealing with those long, complex chains of reasoning that AI often uses to solve math problems. How does OREAL make sense of all that?
That's where the third component comes in.
Okay.
The token level reward model. This part gets really granular.
Okay, break it down for us. What are these tokens and how do they get rewarded?
Think of tokens as the individual words or symbols the AI uses to represent its thought process.
Okay.
The token level reward model assigns a score to each token, indicating how much that token contributed to the final outcome.
So we're essentially zooming in on each step of the AI's reasoning.
Right.
And figuring out which parts were crucial for success
Yeah.
or led to a wrong turn. It's like having a magnifying glass for AI thought processes.
That's a great way to put it. And this level of detail is essential because remember, we're only giving the AI that final outcome reward. Without this fine-grained analysis, it would be much harder for the AI to pinpoint which specific parts of its reasoning were responsible for the result.
This token-level reward model sounds incredibly insightful. It's like peeking into the AI's brain and seeing how it connects the dots.
It's a powerful tool for understanding and guiding the AI's learning process.
Yeah.
And it's a testament to the researchers' ingenuity in designing a system that can learn so effectively from such limited feedback.
Okay, so to recap, best event sampling focuses on the best performing solutions.
Right.
Reward shaping helps us learn from mistakes. And the token level reward model provides insights into the AI's reasoning process. These three components work together to create OREAL, a powerful framework for pushing the limits of outcome-reward learning in math reasoning.
Exactly, and as we saw from the results, it's a remarkably effective approach.
It is.
But there's more to the story, right? The researchers also highlighted the importance of the AI's starting point.
Yes, the importance of a strong foundation. Can you elaborate on that?
They found that the AI's initial policy, its starting point for solving problems, plays a crucial role in OREAL's success.
Right.
Essentially, the AI needs a solid grasp of basic mathematical concepts before it can effectively learn from outcome rewards alone.
It makes sense. You can't build a skyscraper on a shaky foundation.
Right.
You need a strong base to support the complex structure you're trying to create.
Exactly.
So how did they ensure their AI had that solid mathematical foundation?
They pre-trained their models on a massive data set of math problems and solutions.
Okay.
Fine-tuning them to ensure they had a good grasp of mathematical concepts and procedures before even starting the reinforcement learning process.
So it's like giving the AI a crash course in math before sending it off to solve those challenging Math 500 problems.
Right.
Makes sense to me. But beyond that initial training, they also emphasize the importance of diverse and challenging training data. Right?
Absolutely. The researchers found that exposing the AI to a wide range of problems during both pre-training and reinforcement learning was crucial for its ability to generalize and tackle new challenges. It's like training an athlete for a marathon.
Yeah.
You don't just make them run the same route every day.
Right.
You vary the terrain, the distance, the intensity to prepare them for any obstacle they might encounter on race day.
That's a great analogy. It highlights how critical it is to think carefully about the data we feed our AI systems. It's not just about quantity, it's about quality diversity.
Right.
And ensuring we're providing the AI with the right kind of challenges to help it grow and learn.
Exactly. And that's one of the key takeaways from this paper.
Okay.
It's not just about designing clever algorithms. It's also about understanding the importance of data and how it shapes the AI's learning journey.
Well said. Now, I know we've thrown a lot of technical details at our viewers in this first part.
Right.
But hold on tight, because in the next part, we're going to zoom out a bit and explore the broader implications of OREALs.
Sounds good.
Stay tuned, because things are about to get even more interesting.
I'm ready. So we've seen that OREAL can make an AI a math whiz with just outcome rewards, but does it have to stop at math? Could we apply these same principles to other areas where feedback is limited or maybe even a bit messy?
That's a great question, and it gets right to the heart of why this paper is so exciting. It suggests that maybe, just maybe, we can break free from the need for those super detailed reward signals in AI training.
Right.
Imagine the possibilities.
Imagine training an AI to write a compelling story.
Oh, wow. Yeah.
Getting feedback on each sentence would be overwhelming and honestly a bit soul-crushing for any aspiring novelist, human or AI.
Right. You'd want feedback on the overall story, the emotional impact, the character development, not on whether you used a semicolon correctly in sentence 3.
Exactly. And that's where the principles behind OREAL could really shine.
Okay.
Instead of getting bogged down in the minutia, we could train AI systems to focus on the bigger picture, learn from those overall successes and failures, and refine their strategies over time.
It's almost like giving the AI more creative freedom, letting it explore different approaches and learn from its own experiences.
That's a great way to think about it, and this could have huge implications for fields like scientific discovery as well.
Oh, wow, yeah.
Think about designing new materials or developing life-saving drugs.
Those experiments can take forever, and the outcome, like a groundbreaking new material or a cure for a disease, might take years to emerge.
Exactly, but with a framework like OREAL, we could potentially accelerate those discoveries.
Okay.
We could train AI systems to design experiments, analyze results, and learn from each attempt, even if those attempts don't immediately lead to the desired outcome.
It's like having an AI research assistant that's constantly learning and improving, helping us push the boundaries of scientific knowledge.
Right.
Now, you mentioned this idea of messy feedback.
Yeah.
What did you mean by that?
Well, in many real-world scenarios, feedback isn't as clear-cut as a simple correct or incorrect.
Right.
Sometimes it's subjective, nuanced, or even contradictory. Think about training an AI to provide personalized recommendations for movies, books, or even career path.
Right, what one person loves another might hate.
Yeah.
And people's tastes change over time, too.
Exactly.
It's a constantly moving target.
Exactly. And this is where the traditional approaches to reinforcement learning, which rely on those precise reward signals, might start to break down. But a framework like OREAL, which is designed to extract the most learning from limited and potentially ambiguous feedback, could be a game changer in those scenarios.
So instead of trying to define every nuance of good or bad recommendations, we could let the AI learn from user interactions, figure out patterns over time, and constantly refine its recommendations based on those evolving preferences.
Exactly. It's about embracing the messiness of the real world and designing AI systems that can thrive in those environments.
This is all starting to sound pretty revolutionary, but let's get back to the technical side for a moment. We talked about the potential of OREAL, but I'm curious about the challenges involved in actually implementing these principles in real-world scenarios.
Yeah.
What are some of the hurdles we might encounter?
Well, one of the first things that comes to mind is computational cost. Remember, best-of-n sampling involves running multiple simulations to find those best-performing solutions.
And as we scale up to more complex tasks and larger AI models, that computational burden could become significant, right?
Precisely. We need to find ways to make these techniques more computationally efficient so they can be applied to a wider range of problems.
So it's a balancing act between the potential gains from something like best-of-n sampling and the practical constraints of computational resources.
Exactly. And then there's the challenge of reward shaping. It's a powerful tool, but it requires a deep understanding of both the task at hand and the AI's learning process.
Because if we're not careful, we could accidentally introduce bias or mislead the AI with those reward adjustments, right?
That's a valid concern. It's like teaching a child to ride a bike. You want to encourage them and celebrate their progress, but you also want to give them constructive feedback that helps them improve their balance and coordination.
Right. You don't want to cheer every wobble and swerve as if it's a brilliant new technique.
Exactly. So we need to be thoughtful about how we shape those rewards, ensuring they align with the underlying goals of the task and don't steer the AI in the wrong direction.
It sounds like we need a delicate balance of human expertise and algorithmic ingenuity to make reward shaping work effectively.
Absolutely. And then there's the token level reward model. It's an incredibly powerful tool for understanding the AI's reasoning process. But it also presents some unique challenges.
Like what?
Well, for one thing, it's computationally intensive to assign scores to every single token in a complex sequence. We need to find ways to make this process more efficient without sacrificing accuracy.
So it's back to that balancing act again.
Yeah.
Squeezing the most insight out of those token-level scores without bogging down the system.
Exactly. And then there's the challenge of validating those scores. We need to make sure they're actually reflecting the token's contribution to the outcome, and not just capturing random noise in the data.
It's like making sure our magnifying glass isn't distorting the image, that we're seeing a clear and accurate picture of the AI thought process.
That's a great analogy, and it highlights the need for rigorous evaluation and validation techniques to ensure we're not misinterpreting the information provided by the token-level reward model.
So we've got populational costs, the intricacies of reward shaping design, and the need for robust token-level score validation. Those are some serious hurdles.
They are, but I think it's important to remember that these challenges aren't insurmountable. They're simply areas where further research and innovation are needed, and I'm confident that the AI community is up to the task.
That's the spirit. Challenges are just opportunities in disguise, waiting for brilliant minds to come up with solutions.
Exactly, and this paper is a perfect example of that. The researchers behind OREAL have made significant strides in pushing the boundaries of what's possible with outcome reward learning, and their work is paving the way for even more exciting advancements in the future.
Well said. So we've explored the potential of OREAL beyond math, discussed the challenges of implementation, and affirmed our faith in the ingenuity of the AI community. But before we wrap up this part, I want to shift gears for a moment and address something that's often overlooked in discussions about cutting-edge AI research.
You're talking about the practical implications, right? How these advancements actually translate into real-world applications.
Exactly. It's easy to get caught up in the excitement of new algorithms and impressive results, but we need to remember that the ultimate goal of AI research is to develop technologies that benefit humanity.
Absolutely. It's not just about publishing papers or achieving state-of-the-art performance on benchmark datasets. It's about creating AI systems that can solve real-world problems, make our lives easier, and help us understand the world around us better.
So let's talk about that. How do we bridge the gap between research and real-world impact? How do we ensure that these cutting-edge techniques like OREAL actually make their way out of the lab and into applications that make a difference?
That's a crucial question, and I think it involves a multifaceted approach. First, we need to continue pushing the boundaries of research, exploring new ideas, and developing more powerful and efficient algorithms. But we also need to focus on making these algorithms more accessible and user-friendly.
So it's not enough to just publish the research in academic journals. We need to create tools and resources that allow developers and practitioners to actually implement these techniques in real-world projects.
Exactly. We need to develop libraries, frameworks, and APIs that make it easier to integrate these cutting-edge algorithms into existing systems or build new applications from scratch.
It's like creating a bridge between the world of research and the world of practical applications.
That's a great analogy, and building that bridge requires collaboration between researchers, developers, and domain experts. We need to break down the silos between academia and industry and foster a culture of knowledge sharing and open source collaboration.
So it's about creating an ecosystem where researchers can share their latest discoveries, developers can experiment with new tools, and domain experts can provide valuable feedback and guidance on how to apply these technologies to real-world challenges.
Exactly. And as this ecosystem matures, we'll start to see more and more real-world applications of these cutting-edge AI techniques.
I'm already imagining the possibilities. We could have AI systems that help us personalize education, optimize healthcare treatments, design more sustainable cities, and even explore the vastness of space.
And those are just a few examples. The potential applications of AI are truly limitless, and as we continue to develop more efficient and powerful learning algorithms like OREAL, those possibilities will only expand.
That's a truly inspiring thought. Now, I know we're running short on time for this part, but there's one final aspect I want to touch upon before we move on to the next section.
You're talking about the importance of a strong initial policy model, right? We touched upon that earlier when we discussed how the AI needs a solid foundation of mathematical knowledge before it can effectively learn from outcome rewards.
Exactly, and I think this concept has broader implications beyond the realm of math. It suggests that even the most sophisticated AI systems need a good starting point, a foundation of knowledge and understanding that allows them to effectively learn and adapt to new challenges.
You're absolutely right. It's like teaching a child to read. You wouldn't start by throwing them into a Shakespearean play. You'd begin with the alphabet simple words and gradually build up their vocabulary and comprehension skills.
Exactly, and the same principle applies to AI. We need to provide these systems with the right kind of foundational knowledge, whether it's in math, language, science, or any other domain, to empower them to learn and grow effectively.
And this raises an interesting question. How do we determine what constitutes a strong initial policy model for a given task? How do we know what kind of foundational knowledge is essential for the AI to succeed?
That's a great question, and it's one that researchers are still exploring. It's likely to vary depending on the specific task, the complexity of the domain, and the capabilities of the AI system.
Exactly. But one thing is clear, the initial policy model plays a crucial role in shaping the AI's learning trajectory. It sets the stage for what the AI can learn, how quickly it can learn, and ultimately how successful it will be in achieving its goals.
It's almost like providing the AI with a map and a compass to guide its exploration of a new and unknown territory.
That's a great way to put it. And as we develop more sophisticated AI systems capable of tackling increasingly complex tasks, the importance of that initial guidance, that foundational knowledge, will only become more crucial.
Well said. All right, listeners, we've covered a lot of ground in this part. We've explored the potential OREAL beyond math, discussed the challenges of implementation, and highlighted the importance of translating research into real-world impact.
And we've also touched upon the crucial role of a strong initial policy model in shaping the AI's learning journey. But there's one final piece of the puzzle that we need to address before we can fully appreciate the significance of this research.
You're talking about those impressive results, right? That 94% accuracy on Math 500 with a 7 billion parameter model using only outcome rewards.
Exactly. We mentioned those numbers earlier, but I think it's worth revisiting them now that we have a deeper understanding of the challenges involved and the broader implications of this work.
All right, viewers, buckle up. We're about to dive back into those remarkable results and uncover what they truly signify for the future of AI. Stay tuned because things are about to get even more mind-blowing. Okay, so we talked about all the cool things OREAL could do, but let's not forget the paper itself hit some pretty impressive milestones. Right out of the gate, 94% accuracy on Math 500 with a 7 billion parameter model using only outcome rewards. That's huge.
It really is, especially when you consider that most approaches that achieve similar performance rely on much larger models or more detailed feedback. This highlights just how efficient OREAL is at learning. It's like squeezing every bit of knowledge out of each interaction, making the most of what we have.
It's almost like OREAL found a shortcut, a more intelligent way to learn, And they didn't stop at 7 billion parameters either, right?
Right. They pushed it further with a 32 billion parameter model and hit 95% accuracy, setting a new state-of-the-art for that benchmark. This really solidifies OREAL as a leading approach in this area of AI research.
It's exciting to see how far they were able to push the limits with this approach, but beyond just the numbers, what really stood out to you about these results?
What fascinated me was the emphasis on the starting point. The initial policy model, the researchers found that giving the AI a solid foundation of mathematical knowledge before training with OREAL was crucial to its success.
It's like saying you can't teach someone advanced calculus if they haven't mastered basic algebra first. You need those building blocks. So how do they give your models that strong mathematical foundation?
They pre-train the models on a massive data set of math problems and solutions using a technique called rejection sampling fine-tuning. This ensured the AI had a decent understanding of mathematical concepts and procedures before being thrown into the deep end of outcome-reward learning.
So it's like a boot camp to get the AI up to speed before the real training begins. Interesting, they also stress the importance of using diverse and challenging training data throughout the process, right?
Absolutely. They found that exposing the AI to a wide range of problems during both pre-training and reinforcement learning was key for its ability to generalize and solve new, unseen problems. Think of it like training for a marathon. You wouldn't just run the same route every day. You need to vary the terrain, the distance, the intensity to be ready for anything come race day.
That's a great analogy. It really underscores how important the training data is for shaping the AI's abilities. So we've got a strong initial foundation and a diverse set of challenging problems. Those seem to be the key ingredients for success in this outcome-reward world.
Exactly. And these findings open up some exciting avenues for future research. Imagine applying these principles to even more complex math problems, or perhaps exploring entirely new domains where feedback is sparse or expensive to obtain.
The possibilities are truly mind-boggling. But before we wrap up, I have one final question for you. If OREAL can achieve these remarkable results with minimal feedback, does this tell us anything about how we learn?
That's a fascinating question, and while we can't draw direct comparisons between AI and human learning, there are certainly some intriguing parallels. Think about learning to ride a bike. We don't necessarily need someone explaining the physics of balance and coordination. At each step, we learn through trial and error, adjusting our approach based on whether we stay upright or take a tumble.
We learn from the outcome, from the experience itself. It's not always about having someone break down every detail for us.
Precisely, and perhaps this suggests there's more to learning than just receiving explicit instructions or feedback in every step. Maybe there's something inherently powerful about exploring, experimenting, and learning from our own successes and failures.
It's a humbling thought that maybe AI can teach us something about ourselves and the nature of learning. Well, that's a wrap for this episode of AI Paper Podcasts. We've explored the fascinating world of OREAL, a framework that pushes the limits of what's possible with outcome-reward learning in AI.
We've seen how it works, the impressive results it has achieved, and the potential it holds for a wide range of applications.
We hope you found this deep dive insightful, and as always, we encourage you to check out the full paper for yourself and continue exploring this exciting frontier of AI research.
Until next time, keep learning, keep experimenting, and keep pushing the boundaries of what's possible. 1718 point.